Hi folks, welcome to Paul's Showcase. Today I'd like to do something a little different on the channel, basically talk about quantum entanglement. Now you're probably aware of quantum physics and Einstein's theories of relativity beginning at the turn of the century. Mr. Einstein basically solved a problem which everyone else was having with their thermodynamics and time and whatever. Anyway, I'm not going into all that stuff, but basically we've reached a new problem in the 1930s, and Einstein couldn't figure it out basically. What we have is a calcium atom, which was excited in a laboratory, and it emits two particles. Basically, if we just use this necklace as an analogy, let's say that's your calcium atom there. Two particles are emitted from the same atom, and they travel away from the atom at the speed of light, right? Which is what light travels at, and particles travel away. But those particles, right, were excited in a laboratory, and they're what's called entangled, okay? Now, I'm not actually making this up, because if you check it out here, it's a phenomenon, okay? Quantum entanglement. But anyway, what's fascinating about it is Einstein, as intelligent as he was and an amazing guy, who basically started the whole idea of quantum physics, wasn't able to solve the riddle. And the riddle is basically these two particles, right, will move away. If we just draw them on the board here. Here's your calcium atom, right? And the two particles, one will travel that way, the other one will travel that way, and infinite in time, okay? This one, let's say they travel for 1 billion miles. Between here and here, When we observe this particle here, right, the theory is, when we observe, and it's actually not theory because it's actually proven, when we observe this particle here, and it has a spin in this direction, instantly the other particle has a spin in this direction. Now what we don't know is, how do these particles, with such a distance between them, instantly change their phase, their spin, their angle, how they go through a particular, like if this went through a 90-degree filter, this one would go through a 180 degrees phase change instantly at the same time that this is observed. Now this has been proven by Professor John Bell, actually from Northern Ireland. Came up with an experiment to prove this, because Einstein and Niels Bohr were in argument about this. Einstein said, and this is where I believe he made an error, he said that the particles from the point of emission from the calcium atom, their direction, their orientation, their phase was predetermined. So he has this predeterministic attitude of how this problem is resolved. So basically the particles travel across space, and they know what angle, what phase they're going to be at this point in time, billions of miles away, to go through this particular filter. That information is brought on board with the particle. That's what Einstein said. In fact, he said it was like having two gloves in a box, two separate boxes. When you open this box on the left, you see the left-hand glove. Then you know immediately the other glove is right-hand. That's how he saw this problem. But Niels Bohr said that actually, before you open the box, nobody knows if it's a left-hand or a right-hand glove in there. And only when you open the box, the glove decides to be left or right. That's basically what's happened with Niels Bohr's theory. Okay. Anyway, John Bell decided that we could prove this experiment by using lasers and by using filters and emitting at the speed of light these particles to travel around this experiment And when one went through a 90 degrees filter, we would observe the other one, the other side of the room, or in Copenhagen, the other side of the world, okay? And it was proven that when they ran the test, and they ran it again, and they ran it 10,000 times, because you can do this with light, you just turn on the counter, bang, instantly you have your results. They ran it 10,000. The probability curve of this creating this outcome was almost 100% proven that the particles were entangled. They instantly knew the position of when the other particle was observed spinning downwards, this one would spin up. It's basically like two chess pieces here. Okay, when I turn this chess piece here, no matter how far away they are, okay, so let's pretend this is on Mars and this is in Saturn, right? When I observe, I'm the observer. When I observe this piece going here, instantly the detecting equipment observes this particle going the opposite direction, the opposite spin, the opposite filter orientation, whatever. But it only happens when I turn one, the other turns immediately. And the distance between them is infinite, can be infinite. So how does this happen? How can we have information from this piece to this piece occurring when the fastest speed we know by Einstein's theory is the speed of light, 300 million meters per second, or 186,000 miles per hour. The information it would take for 10 billion years, 10 billion light years would take 10 billion years, right? But we know it happens instantly. So this is the big problem, and it's out there for the moment, and nobody has figured it out how it actually happens. And the amazing thing is, we are also involved in it, because when we as human beings, as an intellect, as an observer, as consciousness, when we observe one particle's orientation, it's only when we observe that particle that it reveals its orientation. When we're not observing it, when I'm looking away, that particle is in what's called a quantum state. Nobody knows where it is or what it's doing. It's only when I observe, when I, as the observer, observe this particle, it shows itself, it reveals itself, it reveals its orientation, and instantly the other one does the opposite. So this was proposed by John Bell, and he done the experiment on a laser machine, and it was later reproduced in France at a greater level, and they used filters that would stop any information coming back. So the distance, the time it took for the particle to travel to one detector in the experiment, they had an optical switch to stop any signal coming back. And these were later increased and more comprehensive to absolutely 100% prove that the particles were not in communication with each other. That's been proven. They ran the test millions and millions of times, and it's come up with 99.99999% proof. So how is this happening? This is the thing. How is this actually happening? Now, our idea of space and time and distance between points and events. You're firing a bullet, it travels in a trajectory, it takes a certain amount of time to go the distance. This is completely upside down now. And I'd like to give you everyone has a different idea how this actually happens. If we just take a sheet of paper here, I mean just point A and point B here, yeah, just 2 points. And I can either travel across these 2 points like this, and it takes a certain amount of time to get across here, yeah. And that's what's happening with our two particles. They're very far apart in space, and it takes time for one to travel that distance. So there's an analogy that these two particles are actually joined together this way. So in the space-time warp, the universe is not flat. So these two particles the only way that they can interact with each other is if they are actually one and the same, touching each other. And the space-time dimension, the two-dimension, is actually joined together by this point here. Okay? So it's like the points are touching in here. Yeah? The points are actually touching in the time, in the space-time fabric, and it's one and the same point. Yeah. And this analogy, this theory or whatever, actually works because it basically says that these particles are one and the same. They can only change instantly because they are the same particle. How is that possible? To travel across 1 billion miles in space and yet be the same particle connected? And my theory is that this space and time dimension is completely distorted in the multiverse, if you like. And these particles actually don't have any distance. It's like basically in a black hole. We know now in a black hole, basically when a star collapses, there's infinite gravity. Now, if you have a chair, for instance, you throw it at a black hole, basically it travels down towards the black hole, the infinite gravity, infinite density, and eventually it gets crushed and destroyed, okay, as you would imagine. But Professor Hawkins, we have him here, Professor Stephen Hawkins actually came up with an idea that he was wrong. Originally he thought that the chair was destroyed and that was it. Okay, there was energy converted and what have you in the circumference of the black holes. Point of no return. But now they believe, and he believes also, that the information about the chair, how the chair was constructed, the atomic values, everything that man has in a thought about this chair, the information about this chair is not destroyed in the black hole. In fact, they believe that the information is transferred back into what's called a two-dimension, like a binary code, a source code. It's not destroyed. It's in the universe, and it cannot be destroyed. So, like this garden gnome here, yeah. The information about this, how it was constructed, the colors, what effect it has, garden gnome, is not destroyed. Even though that falls into a black hole, that information is not destroyed. So this has come to light now, that information and thought are not destroyed. And this is very interesting because where we're going now with science and in all these books, string theory, Professor Brian Cox, for anybody that wants to start off with this physics, he's very good for starting us off. There's numerous books here, which I haven't read them all. I really haven't. I've just read little small pieces, which I select. And basically, the best book out in the market. Can I find it? Yeah, there's this book here. How to Teach Quantum Physics to Your Dog. It's sort of a joke, right? But actually it's quite informative, and everything is layman language to explain the different things. We're only talking about quantum entanglement, by the way. There's lots of different quantum problems we don't know about. For instance, the single slot experiment, the double slot experiment, quantum burrowing, they call it, like when a particle arrives at a point and it hasn't got the energy to go through this point, it bounces off, right? It's like basically a stone hitting a wall, bounces off. But in quantum tunneling, the particle arrives and it goes into the wall a little bit, which is not possible. It's absolutely not possible with the energy levels. But we know that it does happen, it does occur, because when we study transistors and semiconductors, we're able to prove that these interactions occur within the matter structures, the lattice structures. Anyway, we're only talking about quantum entanglement today. But To go back to Professor Hawkins' idea of the black hole information not being destroyed, we also believe now that the black hole, because it's infinite density, right? So basically you have a star maybe 1 billion times bigger than the sun, and it collapses down to the size of a very small dot. Okay. Just let's say we say this here. Okay. So we have a star 1 billion times bigger than the sun, and it collapses down to this density here. Okay, which is basically an infinite density in our concept. That density is so massive and the gravity so great, that the time at that point is frozen, right? Because we know that light is bent by the sun. We've proven this with photographic technology today. We know that the gravity of the sun actually bends light around. Okay, so the position of stars we thought for years were there. They're not actually there. They're a little few 100 miles either side. We've proven this. Anyway, so we know that light is bent by gravity. That's already proven by Mr. Einstein. Mr. Einstein here has already proven that. So if light is bent by gravity, time is bent by gravity. So we also know that because of Einstein's theory of relativity. So if the gravity is big enough, which it is in a black hole because it's infinite, the time will be completely frozen. So there's no time between movement. It's completely frozen. Now, at the other side of the black hole, we also believe now, just like I said, there was 2 points like this, 2 points, yeah, in the universe where the 2 particles were apart but could be joined together in the space-time fabric. Yeah, those 2 particles can be joined together at the same point. Yeah, and basically there's a hole between them. Yeah, one universe is connected to the other universe through this infinite gravity point. Now that's a theory, okay? Quantum entanglement is not a theory, it's been proven. We've proved it on laser beam technology, with laser beam technology and filters. We've proven it on the probability. We can't walk away from that. We cannot walk away from that, and Einstein couldn't walk away from it. And actually it was Niels Bohr who basically was more of a philosopher than a physicist. And this is what's happening. And the reason I'm talking to you today is I want you to think about this. Because basically, science, in the 16th, 15th century, science went away from philosophy. Everything could be proven: gravity, force equals mass by acceleration, force between 2 bodies, for F equals m1 m2 over d squared. We were all happy with these formulas. We didn't need philosophy. We had our theories. We had our formulas. Yeah. E equals mc squared, energy in a nuclear explosion. But anyway, we now know that the more we discover, the more we go into quantum physics and accelerometers and splitting the atom, the more problems we're coming up with rather than solutions. The more insights into new areas. And basically, science, the fundamental physics, the fundamental concept of explaining things by theory, as to philosophy, imagining things and deducing things, and they're basically coming very close together. And this is fascinating, because what this means is that science and philosophy are becoming closer and closer together into almost one science. And we have to have, like Niels Bohr had to use philosophy to resolve this problem with the particle entanglement. Einstein wasn't looking at it in a philosophical way. Now, this, I have to say with respect to Einstein, it's still out there. There's a possibility that he could be right. There is a possibility, but it's very, very small. But this idea that matter as we know it, the substance of things made, is affected by our consciousness. How we observe a particle, has proven how the particle behaves, how it reveals itself to us. This is in the single slot and double slot theory. We know that when we're not observing the particle, it behaves in a wave format. It gives an interference pattern. When we observe it, it behaves like a single particle. Shot. One shot. Okay? Just by the observer. It's by me turning in my head, by me observing, by me turning on a photoelectron device, or whatever. So what this is saying is matter is interacting with consciousness. Now where is that leading us? There's a possibility that if you take that into account, matter is able to interact with consciousness. In fact, some people believe, and I believe as well, that matter is an ultimate form of consciousness. And the second theory that Stephen Hawking's about no matter or no information is ever destroyed, it seems to me that we're travelling very, very fast towards the idea of when a human being dies in a physical form, that their thoughts, their imaginations, whatever they have, any information they've had from the time they were born, is not lost. We know that it's not lost because it's information. And therefore, we're pointing to life after death, life after the physical body. Now, who would have believed this? That the theorists of pure mathematics are arriving at a point where they believe that consciousness is not destroyed after the body is deteriorated after death. So, I just thought I'd put that out there. This channel is about music, but it's also about fantastic scientific innuendos which are out there and they're not resolved. And anything you think about or solution you come up with, it's just as valid as any professor, any physicist around the world, because nobody has an answer and nobody has pure facts on these matters, and there's no wrong answer. Okay, so I just like to say that, and that's all for the show. I just recommend this book here by Chaz Arzel. I'm not getting paid for this, by the way. It's just I really do think this is a fantastic book, and I will be promoting books as I see them. So help to Chaz Arzel. That's all I can tell you. You'll find it on the internet. Okay, that's a fantastic book if you really want to get into this physics and quantum theory. Alright, that's all I'd like to say. And the other thing is, no matter how of a genius Einstein was, and he really was an amazing guy, when you think that he was travelling on a tram in Switzerland, and he got this idea that maybe my time on the tram, from the observer looking into the tram, is in a different frame, and that actually occurred to him. But even he is such a genius, he made an error as regards the quantum entanglement, in my belief, and in John Bell's belief, and in Niels Bohr's belief, and in the probabilities belief as well. So that's all I'd like to say. Thank you very much, and welcome to